So today we're going to be graphing an equation in exponential form. Now, what we've done previously, we've done things like absolute value, we've done linear form, we've done quadratics. Exponential form is similar to linear form in that linear changes at a constant difference, is what we call addition and subtraction. Where exponential form is still a constant change, but it's a constant rate, meaning we're multiplying or dividing. So the only difference is the operation, and we're going to see what that looks like when we do that different operation. The second thing is every graph is going to have what we call an asymptote. An asymptote is when the line is going to approach some value but never quite get there. And so what does that mean? Well, let's take a quick look at exponent rules because we're going to be dealing with a lot of these. We're going to have things raised to the 0th power. So anything to the 0th power is 1, no matter what it is. If I take 100 raised to the 0th power, it is a 1. The second rule is that if I have a fraction, let's say 1/2 squared, what that means is that both the top and the bottom are squared. That works no matter what it is. So a divided by b cubed is going to be a cubed divided by b cubed. And then the last thing is if I have, we've done 0, we've done positive, if I have a negative exponent, so -1, all that means is that the variable or the number is in the wrong spot numerator/denominator wise. So I know that that means that, well, nothing's left up top, so I'm going to put a 1. My a should have been on the bottom. That works. If I have like b to the -2, that just means that b was on the wrong spot. I need to put a placeholder for 1 and put b to the negative, no, not b to the -2, it's now b to the +2. b was in the wrong spot, so I turn it positive and put it on the bottom. That works no matter how you have it. If I have something like, let's say a divided by b to the -3, well, I know that I'm going to do exactly what I did right here and make a to the -3 and b to the -3, which means a is in the wrong spot. A needs to be on the bottom, and b is in the wrong spot. B needs to be on the top. So knowing these 3 rules real quickly will help you a lot with a lot of the work we're about to do in exponential form. So, well, what does the graph look like? Well, the graph has a basic shape of a times b to the power of x. A is the starting height, and b is the growth factor. So if I have an equation, let's say right here, let's say I'm doubling. So each time I take the starting height, which would be my a value of 1, I double it. So 1 becomes 2, 2 becomes 4, 4 becomes 8. It just keeps going up and up and up faster and faster. And this is what we call divergent. It moves away from what we're going to see the other side is going to approach. It's moving away from the asymptote. And if I'm multiplying, I can look at the other direction and say, well, 4 divided by 2 is 2, divided by 2 is 1, divided by 2 is half, divided by 2 is a fourth, divided by 2 is an eighth, is a 16th, is a 32nd. We notice how it's getting smaller and smaller and smaller, but it's never actually going to get onto the x-axis, because can you think of any number when you divide it in half that will eventually give you 0? No, there isn't a number. So this is what we call our asymptote. And I'm going to draw it a little below the line just so you can see that it's there in blue. And we say, hey, y can never be 0. And that's an asymptote. And the idea behind this is even if you have, let's say you have a pizza and you divide it among a larger and larger group of people. Let's say you divide it amongst all the people on the planet. Well, when I take and divide it by several billion, that pizza has gone down from a whole pizza to half a pizza to a quarter to maybe a slice, to half a slice, then you're getting a pepperoni, then you're getting part of a pepperoni. And then by the time we've split it amongst everybody in the population, the amount that you get is so infinitesimally small, it's not even worth eating at this point. We can hardly call it a pizza when you get part of a molecule of a pizza. But you don't have nothing. So you can't have nothing it's just so small and insignificant, you don't even wait in line. You're like, I'm gonna go find something else. Let me go find something like broccoli. LOL. So let's graph a few of these. So when I'm dealing with this, I know that I have my starting height is 2, and I know my rate of change, R, or I guess I should say my B, is going to be 3, which means I'm multiplying times 3 each time. And again, if I look at the other direction, I'm going to be dividing by 3. So let's build a table to see if we can't prove a few of these rules. So I'm going to go ahead and start. I know my starting height should be 2. Let's see if we can't prove that by plugging in a 0 into the equation. So 2 times 3 to the power of 0. Let's see. Anything to the 0th power I know is 1. So that's 2 times 1, or 2. Did we get a starting height of 2? Yes. Let's plug in a few more. So like 1, 2, 3. So that means 2 times 3 to the power of 1. That means 2 times 3 to the power of 2. That means 2 times 3 to the power of 3. Let's see if we can't notice the pattern again. So that means 2 times 3, which is 6. This is 2 times 9, which is 18. This is 2 times 27, which is 54. And lo and behold, do we recognize that we have a pattern? We're going to do this in green, where we said my rate of change, or my growth factor, is going to be 3 times 3 times 3 times 3. Each time we increase by multiplying by 3. So realistically, if you have your starting point, you can just fill in the rest knowing where it's going to go. You don't actually need to work it out every single time. Likewise, if we do it in reverse, if I want to plug in a -1, a -2, or a -3, I know that we're going to have to deal with 2 times 3 to the power of -1. 2 times 3 to the power of -2. And 2 times 3 to the power of -3. Okay? So when I work this out, I know 3 is in the wrong spot. That must mean that it is 2 times 1/3. Now that 3 has a +1. So that's 2 to the 1/3, which is 2/3. Right here, I know I have 2 times 1. The 3 is now a +2 on the bottom. So that must mean it's 2 times 1/9, which is 2/9. And for my last one, I know that's 2. Putting the 3 on the bottom, that's going to be 2 times 1/27, which is 2/27. Let's see if we can notice the pattern going in this direction. So if I'm multiplying going to the right, I'm dividing by 3. Notice how my denominator gets bigger. I'm dividing by 3. My denominator gets bigger. I'm dividing by 3. My denominator gets bigger. Perfect. So if you also notice, your denominator gets bigger when we deal with these negative powers at exactly the same rate as the multiplicative factor got bigger going the other direction. Times 3 divided by 3, times 9 divided by 9, times 27 divided by 27. Perfect. So let's graph a few of these values. I got to go up to 54, so how many spaces do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's perfect. 9 divided by 6 is going to be 54, so I'm going to do these by 6s. Okay. So I know at 0, I am about 1/3 of the way up at 2. 1, I'm at 6. 18. And then 54, we said, was right on the end here. Going the other direction, at -1, I am at 2/3, so right there. 2/9, well, I'm even closer. And then at 2/27, I'm even closer. So that kind of looks like it's just a line, but we're going to go with it. And so let's go ahead and say there we go. And I know I have a starting point right here at 0,2. The other thing that I notice is that my asymptote is right here where y cannot equal 0. Boom. And there we go. We have our first exponential graph. So let's do another one. Now, for this one, what we're going to do, instead of having to build out the entire form, let's see if we can't just use our starting point and our growth factor to kind of manipulate the environment. So I know I have a starting point at -2, and I have a growth factor of 3. So if I build an XY table, I know at 0, I'm going to have a -2. And like what we did earlier, I know I'm going to times 3, times 3, times 3, which means that for 1, that should be a -6. For 2, that should be a -18. And for the 3, that should be a -54. Likewise, in reverse, instead of multiplying by 3, divide by 3, divide by 3, divide by 3. Which means I'm going to leave my -2, but I'm going to put it over 3. If I divide by 3 again, I'm going to leave my -2, but that 3 becomes a 9. If I divide by 3 again, I'm going to leave my -2, and that becomes a 27. That's a lot easier to fill out than this. But regardless, if we needed to prove it, the math would be the same. Let's go ahead and let's graph that. So this looks like a flipped version of what we had up there. So I'm going to go ahead and I'm going to say my y is by 6s again. And I'm going to graph some points at 0, -2, 1, -6, 2, -18, 6, 12, 18, and then 54. The other direction, I just get closer and closer and closer to that value without actually touching. There we go. I have my asymptote right here, where my y is not going to get to 0, but it's going to get really, really, really close. And my intercept right there at 0, -2. Perfect. Well, so having seen that, we know that with factors that are above 1, we know it's divergent. We know these graphs are going to spiral off into infinity. What happens, though, if we have a graph with a factor like this, where it's 1/2? How would that actually look? Well, let's see. I know my starting point on this case would be 4, and my growth factor is 1/2. So xy. Let's see if we can't mathematically see what's going on here. So I'm going to start out right in the middle, and I'm hoping that I'm going to get a 4 because my starting value should be a 4. So I'm going to say 4 times 1/2 raised to the 0th power. Anything to the 0th power is 1, so that's just 4 times 1, which is 4. Perfect. Exactly what we expected. So let's try a few other numbers. So 4 to the 1/2 times to the power of 1, 4 times 1/2 to the power of 2, and 4 times 1/2 to the power of 3. 1, 2, 3. Let's see. We know that with powers, they translate in, so that's just 4 times 1 to the 1 over 2 to the 1, which is 4 times 1 over 2, which is 4 halves, which is 2. What's going on right here is 4, well, that's 1 squared over 2 squared, which is 4 times 1 over 4. So 4/4 is 1. 1 cubed over 2 cubed. So that's 4 over 1/8. So 4/8 is 1/2. Let's see if that pattern that we had previously held. Well, it looks like when it's a factor smaller than 1, I'm not getting bigger, but I can look at this one of two different ways. I'm multiplying by 1/2. Or I can say I'm dividing by 2. Doesn't really matter which. I divided by 2 or I multiplied by 1/2, which is my growth factor. So multiplied by 1/2 is 1. Multiplied by 1/2, perfect. So I bet you if I multiply by 1/2, I'm going to divide by 1/2 over here, which if I divide by a fraction, what that's really saying is keep change flip, 2 over 1. That's just multiplying by 2. So I bet you I'm going to double. I bet you I should get 8, 16, 32. But let's go ahead and try this out. So I have 4 times 1/2 to the power of -1, 4 times 1/2 to the power of -2, and 4 times 1/2 to the power of -3. And this is going to get really cramped right here. So that is 4. Now, if I push that in, 1 to the -1 and 2 to the -1, like what I did right here, I know that I'm going to have to flip them. So why don't I just go ahead and flip it and say that's actually 4 to the 2 over 1, which is just 4 times 2, which is 8. Hey, that's exactly what we said was going to happen. So why don't I just say this is 4 times 2 over 1 squared, which is just 2 squared. So 4 by 4, which is 16. Also good. And 4 times, let's flip this, 2 over 1 cubed. So that's 4 times, let's see, 2 cubed is 8 over 1. So just 4 times 8, which is 32. So again, that's exactly what we expected to happen. If I multiply by 1/2, I'm going to divide by 1/2 or multiply by 2. Divide by 1/2 or multiply by 2. Divide by 1/2 or multiply by 2. Perfect. So let's see, I have a point at, I need to go all the way up to 32. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I did this by 8, those would need to be by 4s. Oh, that's perfect. So my first point is at 0, 4, 2, 1, half. Okay. -1 is at 8, 8, 16, 20, 24, 28, 32. Boom. So we have this. So I have a graph that looks something like this. 0, 4 right there. But I notice that this time it's not spiraling off into nowhere. It's actually getting closer and closer as time goes on to our value. So our value right here is y can still not equal 0, but it's getting closer. So this is what we call convergent. It's getting closer and closer and closer to that value instead of what we saw earlier, where it was getting farther and farther away from that value as time went on. So this is what we call convergent. Eventually, if we can get out to infinity, maybe we might actually get 0. But I want you to go ahead and pause the video. Try out number 7. We've got a negative and a fraction. Try out number 7. When you're done, unpause it and see how well you did. Okay. So what I know here is I'm going to do this the short way. Now my starting value is -4. Now my rate of change is 1/2. So for my x, y, I know that if I can spot that initial value, I know that as I move forward from 1 to 2 to 3, that is going to be multiplied by 1/2, or I'm going to divide it in half. Multiplied by 1/2. Multiplied by 1/2. So half of -4 is -2. Half of -2 is -1. Half of -1 is -1/2. Halfway done. And on this way, I know that I'm going to divide by 1/2, which is really just saying multiply by 2. I'm going to divide by 1/2, which is really just saying multiply by 2. And divide by 1/2, which is really just saying multiply by 2. So -1, -2. So if I multiply by 2, -8, -16, -32. So let's see if I do this by, I think my last one was 4s. I'm going to have 0, -4, 1, -2, 2, -1. Half is getting closer and closer. If I go this way, it's 8, 16, and 32. Boom. So with that, I have my intercept at 0, -4. And I know this time it's increasing, but it's not increasing all crazy. I know that it's getting closer and closer and closer to this point at 0, but I know y cannot equal 0. It's kind of a weird slash through my equal sign. But the idea is that no matter if it's approaching from above or if it's approaching from below, we know this is still convergent. And there you go.